Hello, can you hear me? Awesome, sweet. Let me check to make sure. Yep, we're recording. All right. So I took a look at the questions that you sent me, and I can just go through all of those, and then we can see kind of where we're at. What did you think of this section, or this like chunk of work? We're kind of like getting into like what we're going to be using calculus for, and like doing some like some of these problems can get pretty convoluted if you're not careful about like what language you're going to use. So here, turn the phone on. Okay. Yeah. So some of these problems, and we'll get into like optimization later, can get pretty convoluted if we're not careful. So a lot of this is kind of just managing the. Oh yeah, no. A lot of this trig stuff still gets me. And like triangles, you have to like relearn triangles like every time. So yeah, there's just a lot of information processing, I think, in this kind of sections. So let's get started with, you sent me number 15. Did you figure out 15? All right, so if A is the area of a circle with radius r, and the circle is expanding as time passes, find dA dt in terms of dr dt. So we're going to have this circle. Oh, and this is for everyone catching up from the recording. This is 15 from the homework. So we've got the circle with radius r and area a. And we need to find dA dt in terms of dr dt. But really that's kind of a step one in some problem, which is part B, which is suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate, how fast is the area of the spill increasing when the radius is? And then they give you numbers. So basically we're doing part A in order to solve part B. So let's start with kind of the way that I kind of sort this when I'm solving any problem like this is I kind of say, this is what I know. What is an equation that I have that can relate for me area and the radius of the circle? Oh, that's fine. That's probably going to make it a little hard for you to put in equations, but area relating to radius, the area is equal to pi r squared, right? That's one of like our equations that we have for circles. And then I need to kind of outline what I want from this. And I want to find dA dt. And I want it to be in terms of dr dt. But that's kind of like a qualification. What I really want to find is dA dt. So I could take this equation and I could differentiate it. And I could do so with respect to r, so then I would know how a changes when r changes, but that's not what I want. Now we come back to here. What exactly do we want? I want how the area changes with respect to time. So I'm going to differentiate this equation with respect to time. And this works because A is a function of r, which is a function of t, and r is a function of t. So both of these, A and r, are dependent on t. Neither of those are constants. So this is that like implicit differentiation, basically, that we were talking about, and I think 2.6 was implicit. So I'm going to end up with dA dt is equal to 2 pi r times dr dt. And now I have dA dt in terms of dr dt. So I can use this equation to solve part B. Here I have a ruptured tanker that's spilling. I have the rate of change of the radius of the oil spill, which I can turn into like math lingo. I can say radius is changing with time at a rate of 1 meter per second. So the radius is getting larger by 1 meter every second. And I want to find how fast the area is changing, how fast A changes, which means I want the rate of change of A with respect to time. So how does A change with time? When R is equal to 26. So I have all of the different pieces that I need to put into this equation. If I have dA dt is equal to 2 times pi times r, which we're going to say is 26 meters, times dr dt, which is going to be 1 meter per second. This is going to come out to be 52 pi meters squared per second. And the last part of this problem would just be to check to make sure that this answer makes sense. So if I'm looking at how area is changing with respect to time, I'm looking at meters squared per second. And so the units do make sense because area is measured in meters squared, time is measured in seconds, and so every second that passes, I'm getting 52 pi meters squared additionally. So, any questions about that? Does that kind of make sense? Tell me to speed up or slow down anytime as well. It's kind of hard when there's just the chat box, so. Oh no, don't do that. A lot of these, it's like you can get yourself going in circles. So just always remember that you can implicitly differentiate. And a lot of times I will expand something. If you notice, I wrote down that A is a function of R, which is a function of T, and then is equal to pi R of T squared. That way I know that everything is at its root a function of time or something like that. And so that can kind of help you when you're trying to implicitly differentiate in these kind of long word problems. All right, let's try 22. So this is again 22 from the homework for everyone who is watching the video. So this problem took me a little while to parse through, just like reading it. We have a spotlight on the ground that shines on a wall 12 meters away. So I'm going to start. Oh, I don't have a triangle function. I'm going to have to draw it out like this. Okay. So we have a spotlight, and it's shining from this corner, and it's shining on this wall on the far side. Now we have a man who's 2 meters tall, walking along the x-axis from the spotlight towards the building at a speed of 2.2 meters per second. So I'm going to draw the man. I'm going to draw him. There's the man. So this is kind of the figure that they gave you. And he is 2 meters tall. We know that the wall is 12 meters away from the spotlight. Now we're going to say that the man's walking speed, which is dx dt, is equal to, and this is kind of what we got from the problem. If the man is walking along the x-axis from the spotlight towards the building at a speed of 2.2 meters per second, that is our dx dt, which means that this is going to be x, this length here, and this length is going to be 12 minus x. So that's how we kind of got this figure that they gave us. And then the height on the building is given in y, or the height of his shadow on the building. So one thing that I kind of did before I started this problem is to just make sure that this problem kind of makes sense, because it says that what we want to find is how fast the length of shadow on the building, the height of the shadow on the building, is decreasing when he's 4 meters from the building, which means that if he moves along, so if he's further along, then the height is going to be shorter. And that kind of makes sense if we draw this triangle, because this middle bar, you can kind of imagine that green bar, if it moves closer to that end, then this angle right here, right, this kind of gets smaller, and this height gets smaller. So that's kind of the problem that we're looking at. Do you kind of feel comfortable with like the setup of what we're looking at as the guy is moving this way? Yes, that is something my calculus teacher taught me, and that I do every time. So what I want from this is how fast the length, or the height, how they use length here, how fast the height of his shadow is changing on the building, which we can kind of represent mathematically. It is a rate of change, and it is changing with respect to time. So I'm going to be looking for dy dt. So that's what I kind of want from here. So what we need to do is we need to find some way to relate x and y. Because we know how x is changing, we want to know how y is changing. So the way that we kind of did that is we used like analogous triangles. So this was kind of the tutorial, like step 1, is they had you find a relation between x and y. And so if I have 2 triangles, one that looks like this, and one that looks like this, they're a little wonky just because of the way that I'm drawing, but this is 2. And these are the same angles here. And we know that this is y and this is 12. and this is x. So the triangles that I picked out are this triangle right here, and then I picked out this triangle. And because the angle is the same, that yellow angle, I can say that these can be related by a proportion. I can say that the side opposite the angle divided by like the side beside the angle. Or one way that we could do this, instead of just saying proportional, we could say that the yellow angle, that's not sine, it's tan, sorry. We could say that like tan theta is equal to opposite over adjacent, right? TOA, yeah. So that's 2 over x, and tan theta, whatever this angle is also equal to y over 12. So I can say that because tan theta is the same, 2 over x is equal to y over 12. Are you following me up to here? Awesome. Okay, so now I have an equation that will relate to x and y. What I want to do is reorganize it so that I have something that I can, I don't know, more easily work with. So what I ended up doing is I ended up multiplying both sides by 12. And so I said I had 24 over, or rather 24x to the minus 1 is equal to y. Now I know that x is a function of time. This is x of t, and this is y of x of t. So we're going to do basically a very similar thing that we did before, and that we're going to implicitly differentiate in order to, sorry, I'm running out of colors, so I should always try to color code things. In order to find what the rate of change of y is with respect to time. So do you know what the derivative of 24x to the minus 1 is going to be? This is last week's stuff, I think. Yeah. So if we have 24 x to the minus 1, x is a function of t. Yep, exactly. This would be 24 x to the minus 2, and then dx dt. Minus 24x to the minus 2. Just because we're going to be multiplying by this -1 and then subtracting from the power rule differentiation. So now we have this equation, and we can use that to solve for what we actually want. So we said we want to find dy dt, and now we're saying that's equal to -24 times x to the -2, and we can determine what x is by going back to the problem, and he is 4 meters away from the building, so the distance, ooh, I solved this wrong in my notes. Oops. So the answer that I have in my notes is a little wrong, because he's 4 meters away from the building, not 4 meters away from the spotlight. So in my notes, I took x to equal 4, which is not correct, because x is going to, we have 4 is equal to 12 minus x, so x is going to be equal to 8. So this is going to be 4, and this is going to be 8, so it's not quite proportional with the drawing right now. But, whoopsie daisies. So this is 1 over 8 meters squared. And this 24 here comes from 2 meters times 12 meters. So if we're keeping track of the units, this 24 is also in meters squared. And then we're multiplying by dx dt, which we said up here was going to be 2.2 meters per second. So this is going to be, you can simplify this out into negative 24 over 64 meters squared, so these are going to cancel, times 2.2 meters per second. I got to plug this into a calculator now. All right. And so this is going to be 0.825 meters per second. And that is going to be y t. And the last thing to do is just, negative, which makes sense because dy dt is decreasing, or the height on the wall is decreasing. So the sign makes sense. We've got a negative number indicating it's decreasing. And then our units make sense because the height on the wall of the shadow is going to be measured in meters, and time we're going to measure in seconds. So the rate of change of the height of the shadow is going to be in meters per second. So this problem checks out. Any questions about how I went around and solved that? Oh, the way that I did that, so that happened over in this area. Let me get my, so I said that, here, I will erase this. I said that 2 over x is equal to y over 12. And you were good with that? Awesome. Okay. And then I rearranged it by multiplying 12. So I ended up with 24 over x is equal to y. And then I went down here and I implicitly differentiated it, which means I took the derivative of both sides with respect to t. So that's this d dt. And so whatever I do to one side, I have to do to the other side. So this is, to expand it out just more deliberately, this is d dt of 24 x to the negative 1 is equal to d dt of y. Does that make sense? So this is just this, shoot. Sorry, lost my, this is going to be this derivative that we found, which is negative 24. 24x to negative 2 dx dt is equal to dy. Does that make a little bit more sense? Oh, sweet, awesome. All right, so that is problem 22. Do you want me to do problem 20? Because I saw that you got problem 20, but I can still do it if you want me to go over it. For sure, for sure. I'm going to stick around and do a couple more practice problems just from the book. Feel free to head out, or feel free to stick around. But yeah, also email me anytime and I can totally just walk through problems. So yeah. Do you think you're going to stick around for a couple more book practice problems? No pressure. Sweet. All right, you have a great day. Okie doke. So I'm just going to do one or two more problems from each of the sections, just to do a little bit of practice. And yeah, that's what's up. So from 2.5, I am currently, what page am I on? Let me check. I am currently on page 158. And I'm going to go ahead and do problem 21. So the problem is to find the derivative of the function, and we're given this function g of u is equal to u cubed minus 1 over u cubed plus 1 all to the 8. So this problem kind of deals, or this chapter kind of deals with the chain rule, in that we are going to need to use the chain rule to solve this. What I always do is break it down into what is going on here very explicitly. I will say that the function f of u is equal to u cubed minus 1 over u cubed plus 1. And then the function g of f is equal to f to the 8. And this is the function f of u to the 8. And so that will give me my guidance as I go. Actually, I'll color code this because why not? So this will be g of f is equal to f to the 8. All right, and so then I used a g and f, but we just need to keep track of which one is the inside and the outside function. So this is going to be g prime of f times f prime is equal to the derivative. In this case, we're going to call it dg du. Right? So our goal is to find the derivative of g with respect to u, g prime dg du, et cetera, et cetera. And this is the equation that we're going to use to find it. So the next thing I will do after doing this is we need to decide what g prime and f prime are. So g prime is going to be equal to 8, this is g prime of f, is going to be equal to 8f to the 7th. And then f prime of u is going to be requiring the quotient rule from the previous set of lectures, in which we have we'll call h of u, which is equal to u cubed minus 1, and then over we'll call this j of u, which is u cubed plus 1. So then, of course, we need to break it down even further, and I will say that I write this all out almost every time I solve a problem because I get really easily confused. And for me, at least, it is just easier to have this all explicitly written down so that when I do make a mistake, which happens inevitably, I can very easily go back and find out where it was, just kind of track down my previous steps. And yeah, that's kind of how I do things. So f prime of u is going to be equal to h prime j minus j prime h over j squared, I believe, if I can remember my quotient. I'm always nervous about swapping the minus sign because it does actually matter for the quotient rule because of that minus sign, so I want to make sure that I have the right one on top. I'm like 99% sure I'm correct. Yes, I'm good. Okay. All right. So this is going to be 3u squared times u cubed plus 1 minus 3u squared times u cubed minus 1. So this top can be simplified. This will be 3u to the 5th plus 3u squared minus quantity 3u to the 5th minus 3u squared. So this will be 3u to the 5th, 3u squared minus 3u to the 5th plus 3u squared. So these will cancel and we'll end up with 6u squared on top. I'm just going to rewrite this. F prime of u is equal to 6u squared over 3u cubed plus 1 squared. And I think that that is correct. Okay, so I'm going to erase this work just to make some room. This is all quotient rule stuff. All right, so now I've got my F prime, and then my G and my G prime. And I'm going to put these together in a way that I can get 8 times my original F function. So this is F of u, which is u cubed minus 1 over u cubed plus 1. And this is to the 7th. And then this is times F prime, which is going to be 6u squared over 3u squared plus, not 3u squared, just, I don't know where I got that. Oh, that was maybe a doofus, because j is just u cubed plus 1 squared. Okay. Oof. Where did that come from? Okay. All right. So, yeah. That's, you know, I would write out the answer in some way that looked like this. And call it a day. So yeah, that would be 21 using both the chain rule and the quotient rule. All right. Let's go to section 2.6 now. And this is dealing with some implicit differentiation, which we spoke about briefly when we were talking about the practice problems from the homework that we did, which is basically like implicitly differentiating is like not necessarily the most intuitive thing, I think, that we can do in this class, but is probably one of our more useful tools. So let's do problem 7, I think is the one that I picked. I'm on page 166 right now. So we have this. Right? And we are trying to differentiate with respect to x. And one method we would have to do that would be to isolate y and then differentiate with respect to x, so that we could get like dy dx. But that would be very difficult in this case just because of the function that we are looking at. So instead, we are just going to go ahead and take the derivative of both sides with respect to x. This is d dx, and this is d dx. So we'll end up with, and what basically happens is this is distributed to all of these interiorly. So we'll end up with the function d dx x fourth plus dx x squared plus y, or x squared times y squared. plus d dx y cubed is equal to d dx of 5. And some of these are going to be easier to do than others. This one, for instance, is going to be equal to 0 because there is no x. So we know that if we take the derivative of a constant, we're going to end up with 0. This one, we're just going to take the derivative normally. We'll end up with 4x cubed. And then for the sake of like keeping track of what's going on, we'll say dx dx, taking the derivative of x with respect to x, which will be 1. Then let's do this one next, because here we have y. And what we're going to do is we're just going to take the derivative. So we'll end up with 3y squared, but this will be dy dx. And then we are going to wrap up by doing this one. So this is plus, this is plus. And so the way that this works is we're going to be taking basically like sorry, I just totally lost the word. Product rule, essentially, in that we will have the derivative of x squared times y squared plus the derivative of x squared times y squared plus x squared times the derivative of y squared. So this gets broken down further into, this is going to be 2x dx dx times y squared. And this is going to be plus x squared times 2y times dy dx. So now we have this function. We have 4x cubed plus 2xy squared plus x squared, or let's rearrange this to x squared y dy dx plus 3y squared dy dx is equal to 0. Okay, so we're sitting at a pretty good point right now, but we still don't have what we want, which is, if we go back and write down explicitly what we want out of this problem, we want dy dx. So the way that we're going to do that is rearrange. We are going to subtract 2xy squared from both sides. And we are going to subtract 4x cubed from both sides. Cubed. And we will end up with something, sorry, I'm squishing my book as I go so that I have the room to do this. We will end up with something that looks like this: 2x squared y dy dx plus 3y squared dy dx is equal to minus 2xy squared minus 4x cubed. Now we're just going to factor out dy dx. So this is now dy dx times 2x squared y plus 3y squared and then equal to this same thing from up here. And then we will divide. So we will divide this whole side by 2x squared y plus 3y squared, and divide this side by 2x squared y plus 3y squared. And so our final answer that we're going to get is going to be dy dx is equal to the quantity 2x, or rather minus 2xy squared minus 4x cubed over 2x squared y plus 3y squared. And that will be our answer. Yes, that's what we're looking at. All right. So that's how to do a little bit like more in-depth implicit differentiation than what we did from the previous practice problems. All right. 2.7. Sorry, let me resize my book a little bit. Scroll a little bit. So 2.7 was dealing with some more like physical applications. Physical applications. Where did it go? Okay. And in this section, we have a couple of, there's a couple of problems that I like to do. One of them is number 5, which kind of brings us back to this relationship between the graph of a function and how to like analyze its derivative, which is something that I think is a very important part of this class. So here we have a graph of a velocity function of a particle. So this is 5a, where t is measured in seconds. And so it wants you to determine when each particle is speeding up and when it is slowing down. So what we need to do is kind of define what we're looking at. We know we have a function v of t, and this is a velocity. And we know that v of t is equal to x prime of t, or v of t is the derivative of position. So what we need to kind of look at is what exactly they want from this problem. They want to know when something is speeding up versus when it is slowing down. What does that mean in terms of math? Well, when I read this, I see v of t is increasing, perhaps, or we have a positive acceleration, meaning that if we have the function a of t, which is equal to v prime of t, then if a of t is positive, then we have something that's speeding up. So we have something, a particle that is accelerating. And so we can kind of determine that by looking at here. So from here to here, from 0 to 1, A of t is positive. And the way we can tell that is because the slope of the tangent line is positive. So if I were to draw the slope of the line here, or if I were to like draw the tangent line to the curve, it would look something like that. And if I were to do it at like this point, it would look something like that. If I were to do it at like this point, it would look something like that. But all of these slopes along here, and that's kind of how I visualize what's going on, all of these slopes are positive and approaching 0. And the point at which the slope is equal to 0 is at t equals 1, dv dt is equal to 0. Right? Okay. So at all other points, the velocity is going to be, or the acceleration is going to be negative. So here, from 1 to 2, A of t is negative, which we can tell by the slope of the tangent line. And v of t is positive. So I'm making this distinction between this portion of the graph and this portion of the graph for one important reason. And the important reason is that when we're gauging velocity as it relates, when we're gauging velocity, we have to relate it back to the initial point, because the velocity is the derivative of the position graph. So it always relates back to like the initial position. And so when we have something that's doing quote unquote negative velocity, and it is accelerating in a negative direction, the acceleration is also negative. And we can kind of envision it as speeding up in the negative direction. So I would say that this is speeding up in the negative direction from 2 to 3. And so one other way of writing this down, I think, I know I wrote down a lot of stuff here. A lot of this, I think, was just kind of trying to like get people a little bit more familiar with using position and velocity and stuff like that. One other way to look at this would be to say v of t is positive here and a of t is positive. They match, so it's speeding up. Here, v of t is negative and a of t, or positive, excuse me, and a of t is negative. So they don't match. So the particle is slowing. And then we're going to say here that v of t is negative and a of t is negative, so they match. And the particle is speeding up. And by match, I mean the signs of the velocity and the acceleration match. So that's how I would approach problem 5a. All right, let's do one more problem from section 2.8. And so this problem is dealing with related rates. Find the chapter. see what problems I'm going to do in this. Okay. I think in the past I've done problem 1 just because it's a pretty straightforward way of looking at this. A lot of these problems kind of like disguise what they actually want with like basically like there are word problems, they disguise what they want using words. But 1 is very explicit in saying that we have a cubed and it has a volume and its volume is equal to x cubed because that's the length of its side. So volume is equal to width times length times height, and all of these are equal to x. Our volume is equal to x cubed. And x increases as time passes. So they want you to find dv dt in terms of dx dt. And if you remember the circle problem that we did at the very beginning, this is essentially that same type of thing. So we'll take the derivative with respect to time of v of x of t, which is equal to x of t cubed. So this will be dv dt is equal to 3x squared dx dt. Just like if you remember when we were doing our 2.6 problem when we did implicit differentiation. So that is kind of how that problem works. In that that's how I would do that. I think I might have done it a little bit differently in the book, but that's how I would do it. That is what I would do. Let's try another problem. Oh no, I lost my page. Oh shoot, how did I end up chapter 6? Oh, okay. Let's also maybe do problem 3 just for funsies. So we have each side of a square. So we have a square, and each side, we'll call it x, is increasing at a rate of 6 centimeters per second. So dx dt is equal to 6 centimeters per second. At what rate is the area of the square increasing? So we want to find dA dt when the area of the square is 16 centimeters squared. So when A is equal to 16 squared. So there are a couple of pieces to this problem. First of all, we need to relate area and the length of the side, in which case this is A is equal to x squared. Then we need to find out what exactly our area is going to be. So it's going to be dA dt, or sorry, not what exactly our area is going to be, but what our rate of change of our area is going to be. And this is going to be 2x times dx dt. So now we need to solve. We have dx dt, we were given that, but we don't have x right away. What we're going to have to do is infer what x is. So if A is equal to x squared and A is also equal to 16 centimeters squared, then we can take the square root of both of these and we get x is equal to 4 centimeters. So now we can go ahead and solve this problem. dA dt is equal to 2 times 2 centimeters times 6 centimeters per second. So dAdt is equal to 24 centimeters squared per second. And so a lot of these problems are just this same type of process. How can I relate them with an equation? And then what do I have to differentiate by in order to get, and it's usually time, because usually these are some sort of shapes shifting with time. What do I have to differentiate by to get what I want? That's about all I have for you guys tonight. I hope this kind of helped, and I hope you guys have a great week.